We are ready to go. Okay, just to reiterate, for the second lecture on histogram, you're going to watch the video. Okay, you're going to watch the video and read the book chapter, and you will be ready for the MP6. Okay, so it's already posted and all that. From last semester, even the semester before, quite a few students said that if we teach a little bit more about the matrix formulation and how the optimizations can be done, it would have been more meaningful for some of the students. Okay, and about a quarter of the teams were able to make matrix multiplication work, and about 1/10 of the teams were able to get some real optimization working. So we figured that if we teach more into it, you guys will have better shot at it, and then it will make the project more rewarding. So this is one of the feedback we got from last semester, and so we took that feedback seriously, and so here is a new part of the lecture. So that's why the lectures are a little bit kind of stretched a little bit this semester, but we're trying to make sure that you are equipped to do these things in a meaningful way. So some of the material will be new, so there will be a little bit of rough edge. So work with me, okay? And if it's not clear, ask, right? Okay. So just to refresh your memory, we already covered this part. And when we do a convolution layer, remember we have multiple input feature maps, and we call these channels, right? So there will be multiple input feature maps feeding into the convolution layer, and there will be multiple output feature maps, right, coming out of the convolution layer. And each input and output feature map combination will have one convolution filter or mask, right? So here we show that for a single feature, output feature map, we will have 3 convolution masks. Each one goes from each one is mapping from one input to the output. And the contribution of all these inputs will be summarized and accumulated, right, into the output. So this is a little bit different from the convolution, 2D convolution, because in 2D convolution, we have one input, one output, right? Here, we have multiple inputs, and for each output, we need to summarize all the convolution contributions from all the inputs to the output, okay? So you can still apply most of the principles in 2D convolution, but you will need to be adapted a little bit, okay? So here is a simple example where we have the input and we have the output. So basically, we also have the concept of batching. So this is important because there's a mini batch that we're going to have a whole collection of input images, right? And these input images are given to you as a single batch. So the B index selects one of the inputs, right? Inputs in the batch. And then the channel, the next index is the channel. So this corresponds to the multiple input feature maps that were generated from the previous layers, and these are the sort of the multiplicative the production of more and more feature maps as we go down the neural net. Okay, so that's why at each input of these neural net layers, we're going to have multiple of these input feature maps, and we call them channels. So this is the channel index. So for this one, the channel index will be 0, 1, and 2. And the weight is going to be the combination of the input and the output and the input. So the output feature map 0 and input feature map 1 will have a combined weight or mask of W01. And then there will be K by K elements in this mask, right? So then the output 0 here is the zeroth output feature map. Okay, so that should be clear now, right? So when we do the convolution, what we do is we will take each input. So for example, we'll take the input channel 0, and then in order to get the output element at the upper left corner, so this is 0, 0, we're going to take a small tile, right? The small tile of input feature map elements, right? And the input feature elements will be the size of k by k. So this is the convolution mask dimension, right? So the interesting part is that if you look at the tile of the input tile for generating the output element, the index, the upper left corner index of that input is exactly the index for the output feature map, okay, the element. So in order to generate element 0, 0, we're going to take a tile whose upper left corner is index 0, 0, okay? And also remember that this is a slightly different convolution than the 2D convolution you learned, because we're not generating the same size output. We're using a layer of these elements in the input as the halo elements, right? So that's the reason why this indexing worked perfectly, okay? And this is an important property I want you to remember. Whenever you need to generate an output element in the output feature map, you go to the input feature map, and the upper left corner, okay, the upper left corner of that little tile for the convolution is going to start with the index that's exactly the same index as the output index, output element index. Okay, makes sense so far? Okay, so these are the reasons why I want to kind of quickly go back and review this. So you could implement convolution layer as a, just a convolution computation. And you should be using constant memory for the weights, because the weights are small. The number of elements in the weight is relatively small compared to the input feature maps and output feature maps. So in general, when you have somewhat small convolution masks, such as the 3 by 3, 5 by 5, these masks tend to map very nicely into the constant memory. The exception is that when we have some of these medical imaging applications, like MRI imaging and so on, because the resolution of these images are so high that we tend to have a huge number of weights that we need to use for the convolution. So those applications tend to have very, very big convolution filters, and they cannot fit into constant memory. So, but for this class, we're going to let it, we're going to take it easy on you, and let you use the constant memory for the weights. Okay, and for all the test cases that we're going to give you, they will fit into the constant memory. So this gives you a very big advantage in terms of bandwidth that you have, because the constant memory is so well cached on chip that you practically only need to worry about the memory bandwidth for the input elements. Okay, so this makes the problem a lot easier. And so all the output feature maps can be calculated in parallel in this convolution, right? So just like the 2D convolution, we have a lot of parallelism at our disposal. We can generate every output element independently. Okay, they don't depend on each other. And all the output feature map pixels can also be calculated in parallel. Right now, within each output feature map, all the pixels can be generated independently. So all the rows can be done in parallel. All the pixels in each row can be done in parallel. So there's really a lot of parallelism flexibility that we have in this computation. And but the interesting part is that when you go down the neural net, okay, this is something to remember. When you go down the neural net, you're going to have more and more and more feature maps, but each feature map will be smaller and smaller. Okay, if you look at the Lynette example, you start with 32 by 32, and then you end up with much smaller feature maps in the end, a lot more of them. Why? because these smaller feature maps are actually extracted features, okay, from the original picture. So each one is definitely supposed to be smaller than the original one, but you have a lot of them. And all input feature maps can be processed in parallel. That is, remember, we also need to, when we generate an output feature map element, we're going to be collecting the input, the contribution from all the input feature maps. So we could also produce those contributions from all the input feature maps in parallel. However, when we do that, remember these things are going to be contributing to the same output element, so we will need to use atomic operation. Very, very good, okay? So this, this is something that you really, it should become a second nature to you at this point. Whenever you're parallelizing some inputs who will contribute to the same output or possibly contribute to the same output, you immediately need to begin to think about atomic operations, okay? Now, so we can, we already talked about this, but I just want to kind of refresh your memory to make sure that, spring break is kind of a historical, lamppost for the semester. A lot of students come back from spring break and say, what did he talk about before the spring break, right? So this is kind of a quick refresher about how you can build a basic kernel for the matrix multiplication, for the convolution layer. So we can, design the cache, the CUDA code so that each thread block computes a tile of output pixels, which is exactly the same as a 2D convolution design, right? 2D convolution, we had each thread block to calculate a small tile or modest-sized tile of the output pixels. So the tile width, we can define that as a square tile, and then we have tile width pixels in each dimension. And then we can have the x dimension to map to the m output feature maps. So we can say, okay, the x dimension of our thread blocks will give us the m output feature maps. This is a little bit different than the 2D convolution because we have multiple output feature maps to produce. So we'll give that one of the dimensions. Okay, the x dimension gives us each thread block in the x dimension will be kind of mapped into the output feature maps. And then the y dimension in the grid will map to the tiles of the output feature maps. So essentially we have an output feature map, and the output feature map will have multiple tiles, right? And we linearize those tiles and map them into the y dimension. And you say, why do you do this, Professor Hu? You have 3 dimensions, right? You have 3 dimensions of indices that you can play with. Why do you bother to linearize all the tiles in the output feature map into the y dimension? The reason is there is a natural z dimension for all the mini batch, the batched inputs. So we're going to map the batched input into the z dimension, so that we can process the entire input, all the inputs in the batch in parallel in one kernel. So we can use 3 of these dimensions. The highest dimension z will be processing the inputs in the batch. And then for each input, we're going to have the y dimension to process the output, all the output tiles of a single output feature map. And then the x dimension will be mapped to process multiple output feature maps, right? You can adjust this. You can actually switch some of these around, and you'll have different performance, okay? So this is just, a sample design, and then you should be thinking about, when we map the x dimension and the y dimension and so on, what are the implications? Why you will be changing the memory access behavior or the effectiveness of the second level cache. These are the things that you should be thinking about from now until the end of the semester, okay? Now, so if we look at this small example, this is going to be an intuitive example for you to, to guide your implementation. And when you need to think about debugging and so on, this is going to be kind of your tool. So we are generating 4 output feature maps. Okay, we're generating 4 output feature maps. So we're going to allocate each thread block to one of the output feature maps. So this is the X dimension, right? We're mapping the X dimension of all the feature of all the thread blocks into a output feature map, and then within each output feature map we have these tiles. So we linearize the tiles. This is a row major layout linearized tiles, and we map them into the Y dimension. So the Y dimension will give us the 4 thread blocks that will generate the 4 tiles of the output feature map, right? So this is a very, very simple example, and you can play with the different orientations and different mappings, and then you can write a piece of code for the basic kernel, and you already submitted milestone 2, right? So milestone 3 is supposed to be a GPU implementation, right? So this is the minimal that you should be doing for your milestone 3, absolute minimal. And remember, the milestone 3 is due on April 18th. It's not because it takes so long for you to to implement that first GPU implementation. It's really meant for you to think about a lot of these other alternatives and design your base GPU implementation in such a way that it's easy for you to adapt that into the optimized versions. So that's why we'll give you more time, okay? Don't wait until April 17th and look at the lecture notes and try to implement your base kernel. It's not the best way to do your project. You can choose to do that, you're an adult, but I advise against it, okay? It's not going to give you good results. So this is the host code that will implement a base kernel, and basically it implements exactly what we talk about. So we have the W grid and H grid, which is the the division of the output feature maps dimensions by the tile width. So this gives you the number of thread blocks you need in each dimension of your grid. And then so why this gives you the total number of thread blocks you need in the Y dimension, the total number of thread blocks you need in Y dimension in order to cover all the output tiles, output feature map tiles. Okay, and then you launch your block. The block dim is tile width by tile width, and then the grid dim is going to be M, which is the number of output feature maps. The Y is the total number of tiles in each output feature map, linearized. And then 1 is reserved for the batch, for the indexing into the batch images, when you for your final project. And the convolution kernel can be very, very simple. So basically, you can just generate, use the same kernel to iterate through all the inputs. So every thread is going to be responsible for generating one output element. Okay, one output element based on all the 3 input feature map little tiles necessary to generate that one output element. So this is a little piece of code that is very similar to the convolution, 2D convolution kernel, but you iterate through the channels so that you will accumulate the contribution of all the input feature maps, right, to that element, right? So then we have a base implementation. Okay, we have a very, very basic implementation, and this is something that you should be able to do, when you submit your, next milestone. Does that make sense? Okay. Now let's make sure that you understand what you need to do beyond that. There's some observations about the implementation. The amount of parallelism is quite high as long as the total number of pixels across all the output feature map is large, because the fundamental model of parallelism is the output feature map elements. we are exploiting the parallelism across all these generating all these output feature map elements. So this does match the CNN architecture very well. And each input tile is loaded multiple times. This is actually a little bit unfortunate. So once for each block that calculates the output tile that requires the input tile. Let us remember all the outputs. Okay, all the outputs require input from all the inputs, right? So all the 3 input feature maps that in that example contribute to the output. But if you have multiple outputs, you can turn around and see that each input will be used multiple times, once for each output, right? So because we're using different thread blocks to calculate the different tiles in each output, they will be loading the input into their shared memory independently. So the input feature maps will be loaded multiple times, once by each thread block responsible for the output tiles that this input contributes to, right? So this gives us some limitation about how much we can reuse each piece of data when they are loaded into the shared memory. So we are giving up some opportunities, right? Giving up some opportunities to reuse the input data when we generate these multiple output feature maps. And that fundamentally limits the speed up that we can get from the GPU. So this means that you would actually hear this from many people that most of the convolution implementations are memory bandwidth limited. Okay, and for pretty much this kind of reason. I'm not going to go into the forward pooling layer because we already talked about that. So I want to make sure that I went back and talk about the convolution and then the base kernel and so on, just to kind of make sure that we're all on the same page when you begin your optimization journey. So the first sort of the most interesting optimization that we can make to a convolution layer implementation is to formulate the convolution layer in computation as matrix multiplication. The reason why matrix multiplication is interesting is, one, we have extremely good understanding of how to reuse data and how to exploit the access patterns in matrix multiplication. So matrix multiplication is arguably the most efficient computation that you can do on any of the GPUs. And the second one is precisely because the locality, remember the data reuse of our convolution the base convolution implementation gave up on some of the locality, okay, on some of the data reuse when we generate these different output elements. Matrix multiplication gives us a natural way to reuse that data, to reuse the data when we calculate multiple output elements, okay? So the input data. So this is why it's interesting. It has its cost, and it does also require some very, very careful optimization, because if you're not careful, you could actually end up getting a slower implementation by going with the matrix multiplication route. So this is something, the kind of an analogy that I like to use. So when you have a straightforward implementation that is not very good, then you go back and say, maybe I can take a longer route. Okay, I can formulate it as matrix multiplication. I can use some specialized optimization for matrix multiplication. So essentially, your work process for generating that final piece of code has become quite a few more steps, right? So you know what? In Olympics, you know what? There's something very similar. You can have diving, so low dive, where you have a board, you jump on the board, and then you get certain height, and then you do some flips, and then you get into the water. So the problem is you don't have enough height to be able to do all kinds of nice movements, okay, flips and flops and blah, blah, blah. So you say, okay, let's do this. Let's raise the height of the board, right, to something like a mile high or something. And then you get onto the high dive, and then you jump from the high dive. Now you have, a very, very big, very, very big distance where you can do all kinds of nice flips and so on, right? Have you ever been on one of those high dives? Have you looked down from that high dive? And I did that in Barcelona once, okay? One of my friends managed to get me into the Olympic, the village, and then I went up to the high dive and I took a look. I really couldn't believe anyone is willing to jump out of that thing, okay? So immediately what I thought about is that if I were a diver and I'm about to jump out of that board, my biggest fear is after some flips and so on, I end up outside the pool, right? When you have all these flexibilities and all these, the opportunities to perform, there are also many, many opportunities to hurt yourself, right? So this is the warning that I always give to people when they start to go into this kind of journey of optimization. You will need to go through some suboptimal, choices and so on before you can really hit the best, performance point, okay? So how do we formulate a convolution layer as matrix multiplication? Remember, every output element is essentially a small convolution of input and then sum across all these inputs, right? So it's a convolution. Convolution is just a collection of inner products, right? Every output element is an inner product of a small tile of input elements and the convolution mask. Matrix multiplication is just a collection of inner products. Every output is an inner product of a row of input and column of the other input. So to me, if you look at this convolution here, we have three inputs, right? Three inputs. So the first, the output is the convolution of these four elements with these four elements of the mask, and plus the convolution of the inner product of these four elements and these four elements of the output of the mask, and the inner product of these four elements and the four elements of the mask. So when I add those three convolutions, three inner products together, I actually get a bigger inner product, isn't it? I have the first four in the inner product, but then I have a plus sign here. I have the next four inner product, right, section. I have one more section of inner product. But I add them together. So I just generated a 12 element inner product, okay? So if I do this, if I take the weights, okay, if I take the masks, and I straighten up these masks into a 12 element vector, right? 12 element vector. So 1, 1, 2, 2, 1, 1, 2, 2 here, 1, 1, 1, 1, 1, 1, 1, 1 here, 0, 1, 1, 0, 0, 1, 1, 0 here. This gives me the vector for that 12 element inner product, one of the vectors, right? One of the 12 element vectors for the inner product. Now, if I take the input elements, I take these four, and these four, and straighten them up into 12 element column, a 12 element column of the second matrix, then I have the other vector that I can use for the inner product, right? So this is why it's called unrolling. It takes a little tile here in the input and straighten it up into a section of that column. And then so the column is really just the collection of the three little sections that I collected from the input feature maps. Okay? So now, if I look at this, I have a row of matrix, input matrix A, and a column of input matrix. This is a row of the matrix A for the multiplication, and a column of matrix B of the multiplication. And if I do an inner product of this row and the column, I will produce an element of the output. Okay? So that gives me one of the elements. Now, to continue, remember all these output elements, 14, 20, 15, 24, are produced by all the inputs and these three map. These three. So these three are already here, right? These three are already here. So all I have to do for the rest of the elements is to collect the inputs, okay? To collect the inputs into, into the next three columns. And as long as I collect the elements, the correct elements into the next column, let's say here, if I collect all these little tiles, 2013, 2132, and 2113, I collect all these into the next column, I can use the same row of matrix A and just do one more inner product, one more inner product, and I'm getting the elements of these. I'm getting these four elements. Questions? Does it look about right? Yes?
What's the primary benefit from doing this? Is this because of memory coalescing? Because it looks to me,
yeah.
It doesn't look to me, it
yeah.
is the case.
Yeah. Yeah. Exactly. Yeah.
Increase the bandwidth requirement, so there must be something.
Possibly. Yeah. Yeah. So it's coming on the next slide. But I want to make sure at least the procedure is clear. Right? It's not quite clear why we're doing it yet, but it will be, immediately following this. Okay? So is the procedure clear? The idea is that convolution is inner product. Matrix multiplication is inner product. So as long as we put together the convolution elements into the right order, we can produce a larger inner product in the matrix multiplication. Okay? So this gives us a fairly big continuous inner product in the computation. Okay? So now, I can take the next set of my filters, and I do the same thing and make them into the second row of the weight matrix. And then I don't have to do anything for the input, right? The reason is I can just use exactly the same matrix, but I would use the second row to generate the elements in the second row of output. So all the input matrices are already in the right place. As long as I use another vector, which is from the second set of these filters, I will be able to do the inner products in each one and produce the second row of the output. So let me say one more thing. This is also extremely important. When we look at this weight matrix or filter matrix, I actually didn't do anything. The reason is, if you look at these things, in the memory, when I store this little matrix here, this filter matrix here, it's actually stored in row major order, right? So it's actually 1, 1, 2, 2 in the memory. So they are already in the 1, 1, 2, 2, 4. And I store the next little matrix in the memory, which is row major order 2, so that's 1, 1, 1, 1. And the next one is 0, 1, 1, 0. So when I say that this is a row of the first matrix, I didn't do anything. I'm just looking at it as if it's a matrix. It's the original weight matrix that was given to me, the filters, original collection of filters that are stored in consecutive locations given to me anyway. So I really didn't have to do anything to the weight. If I look at the output, I'm generating the output as if it is a matrix. But the first row of the matrix is exactly the row major layout of my output here. So I actually generated two output feature maps stored consecutively, even though I think I was generating a matrix. Okay? So the only cost is the unrolling of the input feature maps. That makes sense? Okay. So conceptual versus reality, right? This is because of the memory layout, the row major layout that we had in the C. Okay? Now, go back and explain this to your roommate at dinner tonight. Okay? For half of you, when you try to explain this to your roommate tonight, you will probably need to go back and watch the video a little bit. Okay, but that's not that's natural. Okay, it's a random percentage. So make sure that you can really explain this, because this is going to be the heart of your intuition when you do the implementation. Okay, now let's take a look at the matrix multiplication. So let's say we have done the unrolling and duplication, right, into the matrix. So let's say if we take the previous matrix, so these are this is the weight matrix, and this is the input feature matrix. So when we do the matrix multiplication, we can do a simple matrix multiplication. Your MP2, I believe, right? So then you will get the output. You'll get the results. So you will get the appropriate results, and that's fine. Okay, that's just fine. And then you can get all these kind of output elements. Now, when we start to do tiled matrix multiplication, right, MP3, then you start to have some interesting effects. So remember, we could tile the convolution filters, right? So the convolution filter can get into the shared memory, and then we can, have these tiled, elements for the, so this is the tiled input elements. So we load this tile of inputs into the shared memory. We load this tile into the shared memory. And then we do a tiled matrix multiplication. We generate these 4 elements. Something interesting happened here. We are now reusing the input elements when we generate multiple output elements. When we generate the element across the output feature maps. Remember, this is one output feature map and then another output feature map, right? So by having a big enough tile, we will be able to reuse the duplicated input data, okay? But reuse the input data when we generate multiple elements of the output, the elements of multiple feature maps, okay, across the output feature maps. Because remember, the rows in this layout, essentially each row is one output feature map. So by doing this tiling, we are now generating multiple output feature map, same position elements, using the same input elements. So we are now beginning to exploit locality, reuse data in the input across different feature maps. Okay, does that make sense? So remember, when you do the implementation, at some point, you will want to convert this thing into constant memory. Because even though shared memory tiling saves memory bandwidth, it still requires explicit loading, okay? But if you use constant memory for the weights, the constant memory caching is so good that you don't need to do that explicit loading into the shared memory, and that will save you even more memory bandwidth. So that will be one of the optimizations you should do once you get the matrix multiplication implementation working. You should convert. You should do that as an optimization to use constant memory for the weights, so that you can have better performance, and you should be able to see better performance out of that that optimization. Okay, so Carl will be here sometime next week to talk about the expectations of the final report and how we're going to grade your project, right? So he will be talking about the fact that we're going to be looking for certain number of optimizations and how you use profilers and so on to prove that you have got some improvement, or you have run into some challenges and so on. So these are the optimizations, okay, that he will be looking for, right? And he will be giving you even more details next time, okay? So, and if we use bigger tiles, then we can potentially have even more savings, okay? So that's why you can play with different tile sizes, and then each input element is used 2 times in the shared memory, and so on. Okay. So there is an interesting problem with the replication. So the replicated input feature maps are shared among the outputs. So there are H out and times W out output feature map elements. So each output feature map has H out times W out elements, right? Each output feature map. So each requires essentially a replication. So each requires its private little segment, right? Each output feature map is using its own private segment in that unrolled matrix, right? So if we look at this example here, for each output feature map, such as 14, we are generating a private section, right, of the input, private section. This is why, they immediately say there's a duplication, of course. And then, so the total number of input elements after replication is going to be the total number of output elements, okay, total number of output elements times k times k, right? Because each output element requires, k by k elements in its private section. This is independent of the number of output feature maps. This is only dependent on the size of each output feature map, because we don't replicate input across output feature maps. Remember that? We are generating one unrolled matrix for all the output feature maps. Right? They're only going to be used by the different rows, right? Remember the different rows of the weight matrix when we do the multiplication. Okay? All make sense so far? Okay, we're all still together, right? Okay, good. So the total number of input elements after replication will be H out times W out times K. So we already know that. And the total number of elements in each original input feature map will be H out plus K minus 1. Remember, the input feature maps are a little bit bigger, right, than the output feature map. So the original elements in each of the original input feature map is H out plus K minus 1 times W out plus K minus 1. So, that's the original size. If you divide up the unrolled matrix size by the original feature map size, input feature map size, you get the replication factor, right? You get that. So this, for example, if I have a small, H out is 2, K is 2, then, and there are 3 input feature maps or channels, so then the total number of input elements in the replicated input feature map will be the output feature map 2 and 2, and then, we need to have the replication is K is K by K, so 2 by 2 and K by K, and then there are 3 channels, right? So these are the total number of input replicate the total number of input elements in that matrix, in the unrolled matrix, right? 3 of these channels, 2 by 2 in each, original input, the 2 by 2 in each replicated sections, and then we have 2 by 2 output elements, each require those sections, right? So that gives us the total number. And this is very, very important to remember, because in the second exam, we're going to ask you this kind of questions. And if you have the intuition, you're going to be able to answer those questions just like that. But if you don't have the intuition, it will take a while to actually derive these kind of things. Okay? So make sure that you really fully understand what that unrolled matrix is about. And then, so the replicating factor in this case is you can divide it by the original input feature, feature maps. So this is 3 channels, and then each original feature map is 2 plus 2 minus 1 times 2 plus 2 minus 1, right? It's slightly bigger than the output by k minus 1. So this gives you 3 by 3 by 3. So by now you should know that the replicating factor is independent of the channels, right? It doesn't matter how many channels you have. The replicating factor is independent because you have both top and bottom. You can cancel them. It really has to do with the size of the output feature map, right? The size of the input feature map, and then the convolution k by k. When the input and output feature maps are very big, then H out plus k minus 1 will be roughly the same as H out, right? When the output and input feature maps are both very much bigger than k, then the replicating factor will approach k by k, right? But for the smaller, feature maps, the k in that expression is important, so it will be not quite, k by k. So if we look at the replicating factor for this very, very small example, the replicating factor is 1.78. But if you have, very, very big input and output feature maps, the replicating factor should approach 2 by 2, which is 4. It should approach that, that value. Does that make sense? And it's intuitive, right? Every output feature map requires k by k private section. So if the input and output feature maps are about the same size, and they're very big and of the same size, then the replicating factor should be just k by k. Okay, so this is all intuitive. Any questions? So let's go into the memory efficiency calculation, right? But I still haven't really answered. I gave you a kind of a high-level reason why the matrix multiplication could be better, right? Because you have the tiled computation, and in the tiled computation, you can actually use the same input elements, in the shared memory where you calculate multiple of the output elements of multiple output feature maps. So that's why the intuition is that you should be able to get better memory efficiency. So assume that we use the tiled 2D convolution for the input elements, then we already calculated the memory bandwidth, sort of the tiled matrix multiplication memory bandwidth, right? In one of the previous lectures, you already have taken some of these the MPs and exercises and so on. So this is just a repeat of the calculation for a 2D tiled matrix convolution. And then the reduction, so when we use the tiled matrix multiplication, the reduction factor of the algorithm is k squared times tile squared divided by tile with minus k plus 1 squared. So, and the convolution filter weight is essentially unimportant here because, they're usually in the constant memory and they're going to be fairly well cached. So, so this is the kind of if we use this one, we're going to have a reuse factor. So whenever you use the matrix multiplication, you start with a deficit. You start with a 1.78. And then, remember, in matrix multiplication, when you tile, you also can calculate the reuse factor. And the reuse factor is essentially the width of the tile when you have a square. So let's say if you use a reasonably big tile, 16 by 16, then you will have 16 times reuse, right? But you need to divide that by 1.78. So that gives you probably about 9 times or so. Okay. So it's not as good as 16, but it would likely be better than the tile matrix multiplication. And when it gets even bigger, 32 by 32, then you start to have real benefits. And so that's the intuition. Now, it actually gets even better. So this is the next sequence of slides. I think I have enough time to finish. And this is something that all the real high-performance implementation of convolution layers actually use. So let's take a look at some properties of the unrolled matrix. Okay, and so far I hope that you have a pretty good intuition about how that matrix came about, right? The little sections of convolution as part of the columns, and then each column correspond to one of the each column correspond to one of the elements in the output, in each output feature map. So let's revisit this. Each unrolled column corresponds to the need of an output feature map element. Okay, take any of the output feature map. Each of these columns correspond to one of these elements in the feature map. Okay, remember we don't replicate the input for multiple output feature maps. We only replicate them for the elements in the feature maps. So each column here corresponds to one of the output feature map elements. So if you have a H out by W out output feature map, okay, and you have M of those, the H out times W out will give you the number of columns you have in that matrix. Does that make sense? Okay. So we have 4 elements here, so we have 4 columns right here. There will need to be 1 column for each of these kind of elements. Okay? Now, so for an output feature map HW, so the index is H and W, so this is 0, 0, H will be 0, W will be 0. The index for the unrolled column is going to be just a linearized index of HW. So it's going to be just H times W out. This is the width of the output feature map, right? Plus W. So this is the linearized index in the output feature map, but that also gives you the index into one of the columns, index for one of these columns. So whenever I say, where can I find the column? Okay, where can I find the column for generating a output feature map element HW? You say, yes, I know. It's H times W out plus W. Right? Full score. Okay? Make sense? Are we still all together? A little bit of hesitation. But that's what the videos are good for. But any immediate questions for now? Okay. So the most important part of this slide is that whenever I want to find the column for which I will be using, with which I'm going to be using to generate an output element, I take the output element's index within the feature map, I take that index, I linearize it, and I can find that column. Okay? Good deal. The second one is that if I look at the index within each column, now I'm looking at the horizontal, the vertical direction, the y index. Okay, the y index of the elements. I find 3 sections, right? In this example, so the 3 sections correspond to the 3 channels, right? So if I have C channels, we'll have C sections right here, right? Now, each section of the unrolled column corresponds to an input feature map, right? So input feature map 0, 1, and 2. Each section of the unrolled column has k times k. This is that little private section, right? So I have k by k in that little section. So for input feature map C, okay, for input feature map C, the vertical index of its section in the unrolled column will be C times k times k. So for C equal to 0, it's going to be here. C equal to 1, it will be 1 times 4, it will be here. And C equal to 2, it will be 2 times 4, it will be right here. Okay? So this gives us a way for us to find for any input feature map, okay, an input feature map with index C, channel C, I can just multiply that C by K and K to give me the beginning index of that little section in the vertical direction. Okay, in the vertical direction. Still good? Okay, now. So if I need to find an input, the input elements for an output, for generating an output, so for output element H and W, the base index for the upper left corner of the input feature, this is when I need to do unrolling. Okay, so this is where I'm going to teach you how to do that unrolling, how you can actually generate your unrolled matrix from your input feature maps. Right? When I assemble this unrolled matrix, I need to be able to go and say, for each of these output, unrolled matrix elements, where do I find the element in the input feature maps? Yes?
There's typo on the picture. So for the third input feature map, right, and the third row, it should be 0, 1, 3, 3. Right?
Here?
Is that 0 or 1?
You mean this one?
Yes.
And which part?
The first thing on the second row.
The first thing is 0, 1 here.
Yeah, then in the like...
Oh, yeah, this is exactly. Thank you. Send me an email about that, okay? This one should be, oh, wait.
The third column.
The third column here.
Yes, and the third row.
The third row, you mean here?
No, go down. For the third picture, yeah, it should be 0, 1, 3, 3.
Right. So it should be, the third one here should come from here, right?
No, it should from 0, 1, 3, 3.
So it should be from 0, 1, 3, 3, right?
Yeah, it's 1, 0, 3.
Thank you. Send me that email, please. Okay, so, by the way, these typos are cockroaches. You kill them, they still come back. The reason is there are multiple versions of these slides, right? So every semester when we assemble the new slides, and there are multiple people working on these things, and we assemble them. If we're not careful, we have these race conditions. They come back. Okay, so yes, we should do what we preach in our own processes. You're absolutely right. We should use atomic operations. So for the, where are we? Okay, so for each output element, the base index for the upper left corner of the input feature map, as I mentioned, is going to be just the HW, and then you use the channel, right? So when I need to assemble any of these private sections for an output feature map element, I say, which channel am I looking at? And that determines the section, right? And then the section is going to give me, this, inside the section, I'm going to have the H and W index linearized to give me, the element that should be there for, the H and W gives me the upper left corner HW, the upper left corner element index that I need, and I use C to select one of those. So when I ask, how do I find the elements for calculating this 0, 0, I'm going to go and say, when C is equal to 0, I'm going to get these 4. When C is 1, I'm going to come here, and then there's still these 4. So these 4 are, the upper left corner is all 0, 0. Okay? So this is how I can go and find the beginning element of those 3 sections in the input feature maps. Okay, in the input feature maps. Okay? Now, the input element index for multiplication with the convolution mask element PQ, remember in each section, in each of these sections, the elements are going to be this, 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 and I can find these elements by going from the upper left corner and have P as addition to the horizontal index and Q as the offset for the vertical index, so I can find the elements for each of these linearized column elements. So basically, this is how I can go into the input feature maps and find exactly the elements I need in order to fill out this little section here. I know how to find the beginning of each section, and in the input feature map, I know how to find the beginning locations in the unrolled matrix, and I know how to find all the elements inside that inside the feature map for filling in the positions of the matrix. So this gives me a complete formulation about how I can go and collect, right? Collect all the input feature map elements if I need to assemble that matrix, unrolled matrix, right? The key is that they are both linked to the output feature map element in the index. I go from there and I say, in order for me to find all the elements I need to calculate that output feature map, if I were doing convolution, this is where I am. And if I'm going to do matrix multiplication, this is where I am. And then you use the P and Q to kind of traverse the input feature map. You do the little offsets, and then you find all the elements, and you can fill into that matrix. Okay? Now, so this is how we can do the input feature map to the unrolled matrix mapping. And so we for every output element A with index H and W, for every mask element P and Q index, for given C of the input feature map, we can calculate the horizontal matrix index. So this is the unrolled index of the input element that correspond to this combination. This combination gives me a unique input feature map element. I need to collect it into the matrix. So I can calculate the unrolled matrix index as H times W out plus WY, because this is the horizontal index which selects one of the columns. Remember, when I select one of the columns, I'm using the linearized output, okay, output element index. And then when we go into the beginning of the unrolled matrix, we need to find the base for the base. So it's the W base is the C times K times K. So I have C and then times K that gives me either this one or this one or this one, depending on the C. And then the horizontal the index for these the height index for these kind of things is W base. So this is the W base that I have plus the P times K plus Q. So this gives me one of the elements that will be multiplied with the PQ index element. Okay, so this gives me the complete index for both the input element and the output element. So naturally, what I'm going to do is I'm going to just assign the input feature map selected by the batch index, selected by the channel index, and then the input element is going to be H plus Q, P, and W plus Q. So this is the element that we're going to pick, 1, 2, 3, 4 here. So each one will have a P 0, 0, 0, 1, 1, 0, 1, 1. And then I'm going to just assign that element into the batch index, and then H unroll and W unroll. I have the output matrix, output matrix index. I have the input feature map index. I pick the element, put it right in. Okay, and that gives me the path. So this is how you're going to collect the unrolled matrix elements from the input feature map. So if I were going to write a sequential code, this is how it's going to look like. I can generate unrolled X by iterating through all the images in the batch, okay, iterating through for each image in the batch, for each channel in the input image, and for that channel, I'm going to calculate the height index for the for the beginning of that section, so that's C times K, and then I'm going to iterate through all the P's and Q's in that little convolution kernel. So for each PQ element combination, I'm going to go through all the output elements, all the output elements in each feature map, all the output positions. For each output position, I'm going to do the calculation exactly like what I showed you in the previous slide. So why is this a good looping order? Because in sequential code, what we're doing is we're looping through all the output element positions, right? So what we're doing when we generate this matrix is we're actually going to be generating this element, this element, this element, this element. For each PQ position and C position, we're going to generate these horizontal neighbors sequentially. And on the CPU, this is a very, very good, efficient way of generating writing memory. And this gives you all the sequential accesses. And this gives you a very, very good cache performance for sequential code. Okay? For parallel code, so it turns out that you have several layers of optimizations. So this is actually almost perfect timing. So, so far I have talked about baseline, tile 2D convolution implementation using constant memory as the convolution masks, and using these, X, Y mapping, right, to give you the thread block that will process all the input channels together, and then you preserve Z for all the input in the batch. So that's good. And then the next level is matrix multiplication baseline. You can write a input feature map unrolling kernel. So I gave you the sequential code, and you should be thinking about how you can write a kernel to implement that same function. Remember memory coalescing. Okay, so how you choose the parallel dimension, and how do you map the loop indices into the thread indices will affect your coalescing. Okay, when you put together the matrix multiplication, the unrolled matrix, and then you could implement the first kernel with just the tile matrix multiplication for both your mask matrix and your unrolled input matrix. And then you can put the weight matrix into constant memory. You didn't do that for your matrix multiplication, MP, but you can do this as a optimization, and you should get better performance. Okay, and remember the mask, the mask matrix, the masks are going to be quite small, so they will fit very well into the constant memory. And then you can use your tile matrix multiplication kernel, and then you need to adapt it if you use the constant memory for convolution masks. So that will be the next two levels of optimization. Chances are this is going to be slower than your tile convolution implementation, because we're calling an extra kernel to do the conversion. Okay, so that extra kernel will take time, and you may not be able to recover from that time. Okay, it's going to be interesting for you to experiment with it. So the next one is the matrix multiplication with built-in unrolling. You perform unrolling only when loading a tile during the matrix multiplication. That is, we have an unrolled matrix, right? We have an unrolled matrix that we're supposed to be doing tile matrix multiplication. But we never materialize that matrix. It's just conceptual. So during runtime, we're still fetching all the elements from the original input feature maps. We're not duplicating. Okay? However, when we do the matrix multiplication, remember we're loading a tile, right? We're loading a tile of the input. When we load the tile of the input, we don't have a real matrix. No, we don't have a real unrolled matrix, right? What we do is we use the properties and formula I gave you, and when you load the conceptual element in the particular in that unrolled matrix, you actually use the formula to go to the input feature maps and grab the element. Make sense? And this allows you to load these tiles from the original input matrix without the extra kernel. It will make your tile loading a little bit more expensive, but it will not require an extra kernel to produce the matrix. It will save the memory bandwidth. Okay? So we are not doing replication either. So that's why this formulation is usually used for all the high performance CUDNN and so on implementation. Okay? Now, the unrolled matrix is only conceptual, and this is a common trick that many applications use. When you know how, oftentimes you will only have a conceptual database, and then you essentially access that the data structure using a different data structure, but the data structure is conceptual for the ease of formulation. When loading a tile element of the conceptual unrolled matrix into the shared memory, use the properties in the lecture to load them from the input feature map. Now, after this, you should be able to get a better performance implementation than the convolution, 2D convolution implementation. In the previous semesters, turned out that this was not the case, because we actually kind of messed up in our problem formulation. We gave you too small a size image input, and you can actually totally use the load the entire images into the shared memory, and that actually caused a very interesting, a very interesting shift of all the optimizations. This semester, we are going to give you bigger images. And you will not be able to load the entire images, I hope, into the shared memory. But if you manage to still figure it out, we will give you extra credit, okay? So, so come back and then, talk about it. Don't just kind of, hide it from us. We're good people. So, we'll give you extra credit if you figure out some way some loopholes in the data, and we like to understand how you find it. So you can actually do even one more level optimization using more advanced matrix multiplication, which is the joint register shared memory multiplication that we usually teach in 508. And if we have enough time, we will try to teach that particular version by the end of the semester, but we usually don't teach that. So the best teams usually go to the 508 lectures and look at it. We'll make that available to you as lecture notes, okay? But if we have time, I will talk about it, okay? So that should give us perfect timing, okay? Good luck with the project, okay?